Hello. Today we will be talking about the binary search tree. Um, this personally is my favorite data structure. Comes up all the time. Super useful. I personally enjoy this assignment quite a bit. So hopefully you'll be able to follow along and enjoy it just as much as I do. Okay, so again, assuming you're watching this video, you probably have access to the A&M GitHub, which I think is a safe assumption. Um, The assignment is called Assignment Binary Search Tree. You should have gotten to this page before watching this video, so if you haven't done that, please do that. We're gonna go ahead and clone the assignment. So see, like, okay. All right. So immediately looking at the assignment, we're gonna see that we've got a source folder and a test folder, like always. Let's go ahead and open that up in Visual Studio. All right. So here we go. This is the actual assignment itself. Um, let's take a quick glance through our README file and see what's going on. So, the name of the assignment, binary search tree. Quick introduction. There is, in fact, no STD binary search tree. So, for the first time, this is the first homework assignment where we are having you implement a data structure that does not exist in the standard template library. So, there's no ground truth binary search tree to compare any of your work to because the C++ language doesn't support this data structure natively, right? So you're going to be doing, essentially mock STL implementation. So a lot of the functions are named within the STL convention. So you have your, insert and erase as per usual. But it's not like vector, it's not like list. There's no, you can never do hashtag include binary search tree. So I just find that interesting. That's some motivation from the textbook. Here's the definition of a binary search tree. So, binary search tree is a binary tree that has this property that for every node X in the tree, values to the left in that left subtree are smaller and values to the right are larger. So, again, if you don't understand binary search trees, probably brush up on those before trying to code this. This should be pretty obvious, I think, before you start. Another quick note is that we're going to be doing comparisons in this data structure, and the way that we do comparisons will be a little bit different. So we'll talk about that in a second. Kind of hints at it here that um, we have values and keys. So, and again, in this data structure, we're not just inserting elements, we're inserting key value pairs, which we'll talk about in a bit. A little bit past that, we've got functions that kind of, I mean, not functions, but definitions that kind of give you some insight on what the functions are doing. So as you can see, you've got your default constructor, parameters, returns, time complexity, tests, all your basic stuff, all this good stuff. So let's go ahead and scroll past these functions for now. Uh, there's going to be a little bit more information for this last function called print level by level, because this is the most difficult part of the assignment, which we will get to last. So we'll talk about this in a minute, but there's a few paragraphs here that explain this. Again, another disclaimer about the comparator. So we're going to talk about that more a little bit. We got some excellent resources here. So binary tree, Geeks for Geeks, Wikipedia, whatnot. Hopefully you remember how to run tests. If not, I will say this is the only PA so far where I've found that the GitHub documentation, the way that they suggest that you, like the order that you suggest that they suggest your implementation is at least somewhat accurate. So for the others, it was kind of like vague, maybe do this, maybe do that. For this one, you very much literally want to do root, size, default constructor, insert, find in that order. And it's missing. It doesn't say that you need to do clear, but you do. So we'll be talking about that, but you'll relatively kind of be moving in this order, which we'll talk about. We've got some resources for debugging. So there's a main function that gets included with the code. And if we go ahead and look at that real quick, I didn't find this super personally useful when I redid this assignment last night. So I don't think everyone is going to have to do this. But if you are stuck, you don't know why your tree isn't working, but you have implemented your default constructor and let's say your insert function, then this print tree function, which is built for you, this is different than print level by level, should give you a nice idea of maybe what's going what's going wrong. And as a little trivia, these names that exist in this tree are, Teresa, that's Professor Lake, that's the goat. And then you got all of these legendary TAs. I don't need to speak to all of them individually, but if you were a TA and you got your name on this list, you did some cool stuff back in the day. Okay, so let's go ahead and walk through the code and talk about what's going on. So hopefully you can tell right away that we are looking at a templated class once again. So like all of the other data structures we've implemented, this binary search tree is going to take some templates. It's going to take a type for your key, a type for your value, and then those will be combined into your key value pair. And then it's going to take in a comparator, which in this case is default std less. We'll talk about that in a minute. We've got some type name redefinitions. So whenever you see key type, that refers to this template that gets passed in, and value type will again also be this value that gets passed in. So those types should be pretty set. Key compare should be set. Pair will be just referencing std pair constructed around this k and this v. And then we're going to have some more, just easy syntax things. So pointer, constant pointer reference, constant reference, exactly what you would expect them to be. So just, pair pointer or pair reference, Uh, Okay, so the atomic level of the binary search tree is the binary node. This is as far as you can divide it effectively. And so within each binary node, you're going to have one element and then two pointers potentially. So you'll at least have space for two pointers. They might be valid, they might be not, but you're going to have a pointer to the left and a pointer to the right, thus connecting you to the subtree where all elements are less and the subtree where all elements are greater. The binary node constructor is done for you, so if you ever need to create a binary node, you can do so by passing in an element and the two pointers, or you can move in an element and two pointers. Both of those are defined. We've got some more. We got some more type name definitions here. So using node is equal to binary node, and node pointer is equal to node pointer. Feel free to use whatever you want here. I personally don't think it's very helpful to just not say binary node, given that we've got this definition up here very clearly called binary node, but it's up to you. Um, like always, we've got some constructors and destructors. So let me just go ahead and label these for sanity's sake. This is default constructor. Then we got our, let's see, this is copy constructor. This is move, and this is our destructor. See. Okay, sick. Now we got some functions that exist here. And mind you, all of this stuff is so the binary node is a private struct, and all of these are public. And we're going to talk about these functions in a second. But so also we've got the copy operator and the move operator. So I'm going to come back to what these do in just a minute. All right, so now looking at our private functions, we've got an insert with copy semantics, we've got an insert with move semantics. These should be line for line identical, except for the fact that anytime you pass X, you've got to pass it, and this function has an R value. We've got one erase function, which is going to take a key type, so that will be the key of the key value pair, and then a pointer to an element that we are looking at, or iterating, recursing through. We'll talk about that in a second. We got constant node pointer min and max, which these expect you to return pointers to the minimum and maximum elements. You got find, which will return you a pointer to an element that has this key that you're looking for. Contains should be a one-liner, so if your find is written correctly, then contains will basically be, so you just return find params not equal. So that one should be super easy. We got clear. This is going to be basically called in your destructor, and then also and it'll be tested individually for the clear and empty test, and then clone. This will be what you use to make your copy constructor. And then let's see, like I promised before, the crux of the assignment is going to be print level by level. This is the most difficult part. This down here, we're going to talk about this in a second. And then these functions, print tree, viz tree, these are done for you just as debugging tools. You will not be tested on them, and you're not expected to modify them or understand what they do for any reason. I mean, if you want to, knock yourself out. Okay, so now that we talked about the private functions, I want to recap on these public functions that I skipped. So why is it that we have a public min and also, so here we've got a public min function, but then if you look in our privates, we've got a private min function as well. Well, as you can see, the private min function is going to take a constant node pointer t, and this could be anywhere. So theoretically, you could call minimum on a subtree, and you could be searching a subtree here, which we will do in the erase function. Whereas the public minimum is going to call that private function on the root, and it's going to return the element uh, that you return from your private minimum function. So whereas the private min function, as you can see, is expecting you to have a constant node pointer as the return type. This one is very clearly a const reference. So the reason we've got this set of public functions that are named similarly to the private ones is that the private ones are internal helpers, and the public ones call those private ones, but return those private functions with very specific parameters. So like call this private function with this parameter and then reference this element out of it. So it's kind of its own thing. So theoretically, a programmer who's using your data structure might want to use the max function to return the maximum element, and they don't need to write their own class to search your subtrees or whatever it is. So yeah, pretty much the same idea for all of these. Root should just be very simple, so just return underscore root. Contains, calls contains, finds, calls find. You don't have to, if there's no to do here, you don't have to do anything about them. Empty return size is equal to 0, size returns size. Those should be pretty straightforward. Uh, and maybe I glossed over this, but the actual members of your binary search tree is going to be a pointer to the highest node, which in this case will be a node pointer to root. We're going to have an actual member that tracks size, and then our comparator, which should be passed in. So, all right, that being said, let's go ahead and talk about the order of implementation. So the first thing you want to do is your default constructor. Basically, all you have to do for this is to make sure that these values are set to something reasonable. So when you're default constructing your tree, this should be null pointer because there's nothing that it would point to, and your size should be 0, so that should knock out your default constructor. Before your default constructor will pass, you also need to do the root function, so just return underscore root. You need to do, I think, maybe the empty function, but definitely the size function. Um, and I think that should pass your default constructor. So once you've got that working, the next thing you're going to want to do is think about insert. So I'm going to switch to my iPad quickly. Uh, but before I do so, I would like to make some notes about what's going on with this insert function. So as you can see, insert is going to take a const reference x and a node pointer reference t. So let's talk about these things. So a const reference, if we look at our type name block, using const reference is equal to const pair reference. So x is going to be the actual pair, so it's going to be the key value. Um, like the key value pair of the two, and then node pointer reference t is different than just a node pointer. This ampersand is huge. This means that when you're passing a pointer to this function, you are passing the pointer from like the scope that called this function explicitly. It's not just a different pointer that has the same address. And again, waving my hands, take my word for it. I will diagram this in a second. Okay, so now that we know that we're passing in a key value pair and a const node pointer, well, not a constant node pointer, but a node pointer reference to t, um, let's go ahead and maybe start drawing some stuff. So what I've glossed over so far is the default constructor and some functions. Um, let's go ahead and summarize that stuff and then talk about insert. So hopefully you can now see my iPad. All right, so the things that I glossed over before is the anatomy of the binary search tree is built upon the binary node. So let's see, let's go ahead and draw that out here. So the anatomy of the binary search tree it boils down to this binary node. And within the binary node, we're going to have some data, which in this case is called element. And we're going to have a left pointer and a right pointer. And of course, these left and right pointers will be connected to other binary nodes, right? Hence, we get the binary tree and so on and so forth. Um, quick thing to note is that the element is not actually some data type. So it's not just some piece of data that would be very convenient, but in fact, we are going to be having a key value pair as our as our data per se, right? And so what that is, what this key value pair is the key is something that is easy to compare, easy to search for, easy to sort through, and the value is going to be something meaningful that we actually wish to store. So for instance, if we have a binary search tree and we're trying to store strings, we might have something like this. We might have some key being an integer that's easy to search, easy to sort through, but then maybe some huge data type, like maybe we've got like some class called, I don't know, it's called a box class. And imagine this is like some crazy expensive, super huge data type that it would be very difficult to define a comparator for. Then, maybe we want our box to be the data, but we want to actually do our searching and sorting based on this key. And we've got the value just being stored as a product of this key or whatever it is. So actually, if you look in the tests for this PA, the binary search tree is almost always implemented as, so it'll be BST, and then it'll be templated with ints, and then, some comparator. But it's almost always going to be that the first and second values of this element are both integers. So just as a quick note, so let's assume that we've got a binary node pointer. If you do pointer arrow element, that will return you this key value pair. And then if you explicitly do pointer element dot first, that will give you the key. And if you literally do pointer element dot second, that will give you the value. So that will give you this. Where was I going with that? You can basically expect in this PA that most of the tests, both the first and second values that are passed into this element are both going to be integer. But the reason that we still give you the key value pair is just theoretically, you want to exist in a world in which you could have one of the elements of the key value pair be very easy to sort through and the other be relatively expensive and not run into any issues, right? So let me just draw that as a quick example. So imagine we're literally comparing apples and oranges. So apples, and this is our binary search tree. Then, imagine we can't compare apples and oranges, right? Uh, we have to compare their keys, right? And as you can see, we can have a valid binary search tree based on the first of these key value pairs. So maybe that's some motivation as to why we in fact have key value pairs. Yeah, assuming that these comparisons are difficult. So hopefully that clears up kind of what the actual structure of the assignment looks like as far as the atomic level. All right, so I promised we were going to talk about insert. So insert is going to take it's going to take some kind of pair and some kind of pointer reference. And so for the sake of demonstration, now that you know that this is actually what the tree looks like with this key value pair structure, for simplicity's sake, I'm just going to pretend like we're sorting through keys just to make the example a little bit more palatable, right? So theoretically, given this insert function, we are given a pair that we're trying to insert. So this will be like, let's say in this case, we're trying to insert 45, and then, some data, which we don't really care about at the moment. And then we have a pointer reference, and let's say that starts here relatively. So I'm just going to call this pointer. Then the goal of the insert function is twofold. So the first thing that we want to do is we want to actually find the position that we are inserting. So basically the insert function will first find, and then the second goal is we want to actually perform the insert. And so the insert function, if you saw on the GitHub, or maybe I brushed over it too quickly, we expect that you will do all inserts as leaf nodes. So every insert will have to happen at the end of the tree. And when we talk about balancing later in the semester, you can maybe see why this is going to be an issue, right? Because you could theoretically just keep inserting as leaves and then have a very imbalanced structure. But for now, we're not actually worrying about that. So the first goal is to find the null pointer or find the leaf location that the insert makes sense, which in our case is going to be here. So once we've identified this null pointer, we know exactly where it is that we want to put our node, which will be here, right? So the first goal is going to be a recursive traversal. So we're going to diagram that out in a second. And then the next goal is that once we've actually found this pointer, then we're going to do the insert. So let's go ahead and write some pseudocode. So insert, oops. So insert with your pair and your pointer reference is going to look something along the following. So if your pointer is null, then that's a good thing because that means that we found the location. So actually perform, yeah, actually that's ambiguous. I'm going to say allocation, and we'll come back to this. So assuming that your pointer is the null pointer, that means that we found the leaf or the position that we need to insert. Or imagine that your binary search tree is in fact empty and your root node is a null pointer. If you call insert and the first thing that you're passed is a null pointer, then congrats, that's where your node goes. So that's just a quick aside. All right. So we'll come back to this actual allocation step, but for now, let's talk about traversal. So assuming we're not looking at a null pointer, we need to make a decision. So if we start with a pointer to this node, which in this case is 42, we need to compare this key to the key from the pair that we're given. And then we need to make a decision as to whether we're traversing the left side of the tree or the right side of the tree, which in this case is going to be done with the comparison function. So again, I'm sorry to wave my hands and say, take my word for so much. There's so much explanation that needs to go before we talk about this, but let's just for now assume that the comparison is a less than function, which I think it literally is. So else if compare, and then so if the key that we're given, so this our key, so I guess this is going to be pair, oops. So if pair dot first is in fact less than let's see, pointer element first. So pointer element first. And this is a little bit sloppy also, forgive me. So if that's true, so if the pair that we're looking at, which in this case is 45, is less than 42, then we need to go to the left of the tree. So that would be like literally just a recursive call. So insert same pair, different part of the tree. So pointer right. And then, of course, because this is a recursive call, that's just going to start this process all over again until eventually we get to the point where pointer is null, and then the insert will happen there. So assuming that that's true for that case, it should be the exact opposite. So if we do comparison and then the different ordering, so if we do pointer element first, turns out to be less than pair dot first. Again, this is sloppy, sorry. But assuming that, let's see, what did we say? Pointer element first is less than the pair that we're looking at. That means we need to move right. So again, same idea. We're just going to be recursively calling this insert function, but on the right subtree. So insert same pair, but now oh, did I say right before? Oh man, I'm so sorry. I think this was left. Or if I mess this up, y'all, just diagram it out on paper. I'm sorry. I'm trying to move quickly here. So see if the pair first is less than, then you move left. Yeah. I think that makes sense. Okay. 6. So assuming that neither of these comparisons are true, there's still a case in which the key that we're looking at is exactly equal to. So in the case that it's equal, you actually want to set the pointer second value to the new value. So pointer element second is equal to pair second. And that's essentially like saying if we found, for instance, if this root node was, and forgive me for moving a million miles an hour, but if this root node was the same, if we had the same key here, then all we need to do is, so this is 45 and apple, and we try to perform an insert with 45 and orange. Then all we need to do is replace the data that is already there. So hopefully that makes sense as some pseudocode. Now I skipped this. Skip this step. We need to talk about this. So what actually happens? So assuming that we found the null pointer where the insert needs to happen, which is in fact here, uh, then we need to allocate a new node. So we need to allocate a new binary node. But there's still the issue of how do we connect this node, which is currently a leaf, to the last node that saw it, right? And so before I can answer this fully, we need to do a discussion about what this means. So what is the pointer reference? So, and again, I'm so sorry for all of the sidebars, having talked about so much ridiculous nonsense before we even like finish the insert function, but bear with me. So let's imagine that we've got some binary search tree, right? Uh, and let's imagine that we've got a pointer to the root. So let's say we've got just a regular vanilla pointer. And when I mean vanilla pointer, I'm going to define that as binary node pointer, right? So when I say vanilla pointer, I mean it's literally just a pointer to a binary node, right? What this is going to do is this is going to store some address. So pointer explicitly is going to be some, some nasty address that actually exists in memory, right? And if we were to do an operation like, let's say pointer is, oops, pointer is equal to pointer right, then all that happens is, so right now we said this pointer stores some address. Let's call it this, right? That's not a real address, but just call it that. If we say something like pointer is equal to pointer right, then that just has the effect of changing which address this pointer stores, which uh, maybe that's maybe that's this, right? Maybe that's just some new address, right? And if we do it again, so if we run this line again, then same idea, we're just changing what address this pointer actually has access to. So again, this could be any address. We don't really know, don't really care. All right. So uh, that being some background on actual pointers, let's talk about the pointer reference. So if you see something that is like binary node star or node pointer in our code, and then it's followed by this ampersand, let's call this pointer ref. Um, and actually, let's just keep calling it pointer for the sake of this, whatever. This pointer reference is a pointer alias, right? So it is just a way of renaming a pointer that already exists. So let's assume that pointer reference was this pointer here, right? So assume that this is pointer, right? So this is pointer. Because we have an alias to that pointer, right? So this pointer right here, right now is storing some kind of address. So it'll be, whatever the address of this is. We should don't need to talk about that. But so because we have an alias to this pointer, then we can change what that pointer points to, and that will be consequential to the rest of the data structure. So again, I'm trying not to make this more confusing than it needs to be, but assuming we've got a pointer reference, being the actual pointer, not just being some spot in memory that stores the location, if we change this pointer, that changes the actual data structure. So if we were to run pointer is equal to pointer right, then that would be like changing this actual pointer. So that would be like doing this. Okay. Right. So pointer is equal to pointer right would be like taking the pointer that exists in the data structure and then saying you have this new address now. So uh, again, I really don't want to make this concept too complicated because it's basically just it's the same idea as we had before, right? With a pointer, you're just like taking some address that did exist before and you're substituting it out, except now when you've got a reference, instead of just traversing the data structure, you're actually changing the pointer that you are quote unquote referencing. So hopefully that makes a little bit of sense because we did pass a pointer reference to our insert function. And why did we do that? Well, we did that because let's walk through a hypothetical here. So hypothetically, if we are using a non-pointer reference, then that pointer is just going to hop from element to element as we traverse the tree. So if we've got, let's call it pointer. So if we've got a non-pointer reference, then this pointer is just going to hop every time. Oops. It's just going to hop every time we move it. It'll just be this, and then it'll just be this, and then it'll just be some null value. And if we do run into this situation where we're just using a vanilla pointer with no reference, then when we allocate, so let's go ahead and actually say this for sure. So let's say binary node pointer, uh, and then calling the actual new keyword, so binary node, and then you'll have to actually pass something to this constructor. But so when we actually do this, uh, then so what, right? We've got some new node that's just floating out here. So we've got new node, which is this. And in order to connect its predecessor, we would then have to go and traverse the entire data structure again to say, okay, well now 50 points there, right? Which is not efficient because we did all this work and finding this location. So why should we have to find it a second time? And this is kind of the issue that the pointer reference solves. So instead of pointing in a pointer, I mean passing in a pointer that just happens to store the right address, like we were talking about before. So just assume that this is the right address, right? Instead of doing that, if we pass in a pointer reference, that's passing in this actual pointer, right? So assuming that this pointer reference is null, this is the pointer that needs to receive the allocated node from the heap. So if we call this pointer reference, then pointer reference should receive this new binary node. So again, I'm sorry for the length that it took me to actually explain this, but hopefully that should maybe clear up what the difference between the pointer and the pointer reference is. They both kind of have the same idea because they both store an address, except for the difference being that the reference is an actual part of your data structure because it's like a reference to a pointer. Um, okay. So again, apologies for hammering that in so thoroughly. Hopefully that gives you some kind of intuition. Um, All right, so now that we have talked about inserts in pretty great detail, let's go ahead and move on. So once you've done your insert, then the insert and count function should pass. And after that, you're going to need to do your find function, which is here. And I'm not actually going to write pseudocode for that because if you've done insert, then the logic that we did before with the comparator should be, pretty much good to go, I think. Yeah, so you should be able to do this one yourself, I think. Probably not too difficult. And then once you've done these, insert and find should pass. Oh, I forgot to mention something. So your insert function, the test case, will actually not pass until you've done your destructor because it's keeping track of how many allocations happen, and then it's setting that number of allocations equal to the deallocations and hoping that those two numbers are equal. So before any of the insert stuff will pass, you also have to do your clear function. And then you can call clear in your destructor. So your destructor can literally be this. Let's go ahead and talk about that. All right, so One thing that you need to understand about the nature of a tree in order to do the clear function is something called post-order traversal. So post-order traversal. Okay, so post-order traversal is just one of the traversal methods of a tree. So imagine we've got some kind of functions. Let's call function post. And this is just pseudocode, so forgive me, right? And let's say that this post function is going to recursively call itself. So, uh, and let's actually pass it a pointer. So pointer. So first it's going to run post on the pointer left, and then it's going to run post on the pointer right. And then it's going to actually perform some other function call, right? And so when you define a recursive function in this way, and you say first recurse through the left, then recurse through the right, and then only after all of those recursions have happened, then you do some other function call. That's known as post-order traversal. And essentially that has the effect that if you have a binary tree, and let's just go ahead and draw out a binary tree. Uh, so if you have a binary tree, that has the effect that the function call only happens on the nodes whose children have all been visited by this said function, right? So that means that theoretically the leaf nodes are going to have this actual function call happen before the parent nodes, and by extension, the very last function call should be performed on the root node. And that type of behavior is very well suited for clearing a tree, because when we're trying to clear a tree, we don't want to just do this, right? Because if we delete the root node, then we've lost the information that leads us to the rest of the tree, which we need to deallocate those nodes as well, right? So it would be a mistake to deallocate a node before we have seen all of its children. And that's kind of the thinking here behind using post-order traversal to implement the clear function. So I said it's some other function, but let's go ahead and call this clear just to make it obvious what's going on. So some function clear. You should first clear the entire left subtree, and you should clear the entire right subtree, and then you should delete. Not an English major. Delete pointer. So, assuming you follow this order, and that means that by the time you're actually getting to this delete call, you are guaranteed to have already cleared everything else in the rest of the tree. So, if we follow this pseudocode that I wrote here for the clear function, let's just go ahead and try to track this. So we're going to call clear on the root. Um, and that's going to make us do these two recursive calls. So first we're going to have to clear the left subtree, which we can do because this one doesn't have any children. And then we have to clear the right subtree. So that will look like this. And then we're going to clear this node, and then this one, and this one, right? And so that kind of has the effect that we essentially do this bottom-up destruction such that we don't actually destroy any nodes who have information on how to get to other nodes that we still need to visit. So post-order traversal, clear function should be implemented in that way. Uh, Okay, so once you've done that, then that behavior that I just described should be like exactly what needs to be done for the destructor. And maybe as a quick note, there is a public and a private clear function. So the post order nonsense that I just said, that goes here in your private function. And then for your destructor, this will be calling your public clear, which will call your private clear on the root. So it'll clear everything below the root and set size equal to 0. So should be pretty straightforward. And once you've done that, then insert and count, insert and find should all return positive from the test cases. So that being said, next thing to implement is probably contains, minimum, and maximum. So let's go ahead and talk about that. So again, contains should be very easy. If you've done find, it should be essentially a one-liner. Minimum and maximum. So binary trees have got this wonderful property that everything to the left is less and everything to the right is greater, right? And so if we are to look at a subtree, so imagine we were to divide this tree and say we're looking at this subtree. One of the interesting properties is that given that this subtree that I circled in green is to the left of this node, that's like saying that everything in the subtree is less than this other part of the tree here, right? And so if you keep defining subtrees, right? So you keep, okay, well, I'm looking at this subtree, so now this must be less than everything else out here. You run into the truth that if you go as far left as possible in your tree, this is the minimum element, right? So this will be your minimum element. And you know that it's the minimum because if you've gone the farthest to the left, which means that there can't possibly be another element out here to the left, and if there was, then that would just be the furthest to the left. So if you've gone the furthest to the left, you know that this is the smallest element because anything to the right has got to be greater than this element by definition, and everything else that we've seen before also has to be greater. So that gives us the properties that the minimum element will always be the leftmost element and the maximal element will always be the rightmost element. So I'm not going to give you pseudocode, but hopefully you can see how your min function and your max function could be done rather quickly if you just recursively call the min function on either the left of the pointer or the right of the pointer until you get to a null pointer, in which case you found your minimum or maximum. So hopefully that should be pretty fair game. All right, so that's minimum and maximum. The next big thing that needs to happen in your code is going to be probably the erase function. So again, this is non-trivial stuff. The erase function is definitely non-trivial. So let's go ahead and talk about what needs to happen for uh, erase. Let's look. So, where are we? Yeah, so erase is going to take constant key type X and a node pointer reference T. So looking at this, we can see that we're given a key. So we actually have to find the position from the tree that we're trying to erase, just like we had to find the position in the tree that we're trying to insert. Um, and then we're given a node pointer to either the tree or the subtree that we're looking to erase this element from. So like insert was two parts. Like I said before, this kind of the one part which is actually inserting the node, and then there's the other part which is finding the position to insert the node. Erase is also going to be two parts in the sense that you have to find the position of the node that you're erasing, and then also you have to perform the erase. So uh, let's go ahead and talk about that. Um, okay, so where are we? Talking about erase. So erase is going to give you a key type, and it's going to give you a pointer reference. Okay, so first, and let's just go ahead and draw our example tree like we usually do. Okay, so you're given some pointer reference, so just call this our pointer reference. Erase is going to have two purposes. The first purpose is to find. So the same nonsense that we did up here for insert. So basically calling the comparison function. So if we need to go to the left, then we recurse to the left. And if we need to go to the right, then we recurse to the right. Otherwise, we found something that's equal and then we do something. That logic is going to be pretty much identical for your erase function. So erase is going to look like some series of if statements. So, if comp and then your elements, then you want to iterate to the left, right? And then likewise, if comp with the elements flipped takes you the other direction, then you want to erase the other direction. Else, if neither of these things happen, so if one is not greater than the other, then you are guaranteed that the two elements are equal. So in fact, key and the first value of this pointer reference, if those are in fact equal, then this is where uh, the actual erase happens. And so a quick note on logical operators, which I think I just kind of blew through here, is that logical operators can be combined to create each other. So super quick note on Boolean operators. So if you've got something like A is less than B, then the opposite of this, so um, not A is less than B, is pretty much equivalent to A is greater than or equal to B, right? Because theoretically, a logical expression, so if we've got some kind of expression and its inverse, between these two things, so you've got the expression and its inverse, between the two of those, everything in the entire universe needs to be included between these two. So if we've got some Boolean statement, such as A is less than B, and then some also Boolean statement like A is not less than B, then between those two, every possible combination of A and B needs to fall into one of those two categories. And so when you use the logical negate on something like A is less than B, what you're left with is A is greater than or equal to, because uh, the case in which A equals B can't just be floating, right? Because if you have the logical expression and its inverse, every possible case needs to be accounted between the two, which is why the equality case gets counted in the inverse. So again, that's some discrete math stuff. Probably don't worry about that too much. Maybe you can like derive this as a proof just for fun. But quick point that I want to make is that you can construct an equality operator using this phenomenon. So if you know that A is not less than B, and you know that B is not less than A, then you know that the two are equal. So this is more or less equivalent to A is equal to B. So in the code here, if you've decided that A is not less than B and B is not less than A, then you know that the elements that you're looking at should be more or less equal. So while you do have to use this comparison comparator, this comp, for this assignment, and you're not actually given an equality operator, so there's no way that you can actually check in one line explicitly if with one operation, if the key that's being passed in matches the key that the pointer points to. If you get past these cases, so if you get past the first comparison and the second comparison, you know that you're looking at the right element, which in this case is the one that you're looking for. So that being said, that's just a quick little aside, which I feel like is probably adjacently helpful. Okay, so anyways, assuming that we found the right location, so imagine we are trying to erase this node right here, and we've recursed until we've gotten there. What needs to happen? Well, within the erase actually happening, there's a few different permutations that are possible. So the first thing that's possible is we've got no children, and this is the easiest case for erase. So if we're erasing this node that has just these null pointers here, no children, then it's not going to mess up anything below the tree if we delete this node, right? Because this node doesn't store any information about other data in the tree because it has no children. So just delete and probably like size minus minus, and then maybe like throw a null pointer in there or something. But this should be relatively easy. So that can be accomplished just by deleting this node and invalidating the pointer that it pointed to. So that is pretty easy. That's the first possible permutation. The next permutation is what happens if we've got one child. So I'm just going to go ahead and redraw this example. So if this is the node that we're looking at, and we've got one child, so actually for the sake of example, let's go ahead and stop. So if we've got one child, as you can see, one of the pointers is null, but the other one is valid. We've got one child. Then what needs to happen here is we essentially need to do the linked list erase, or we need to actually perform the skip, right? And let me be completely consistent. Because we're using pointer references, then pointer itself, so this is the element that we're erasing. This is going to be pointer. So it's an actual reference to the element. So given that we've got a pointer reference, so hopefully you remember my explanation from before about the differences between pointer and pointer references. So I'm not going to go over that again, but assuming that we've got a pointer reference here, then the skip should be pretty easy because we have a reference to this actual pointer. Let me just oops. Just trying to more neat. So because we have a reference to this actual pointer, then we can do something like pointer is equal to pointer next, and that changes this actual pointer. So this is now pointer, and that means that we can now safely deallocate this node right here. And as you can see, this connection is preserved. So before we do that, though, probably a good idea to perhaps, let's say, node pointer temp is going to store this value, and then pointer is equal to pointer next, which in this case is either left or right. So I'm going to leave that as an exercise to you to figure out, and then we can safely delete this thing that was here at temp, and we're good to go. So the last permutation is what happens if there's two children. And so get some more space. Oops. Apologies. Apologies. Okay, so where are we? So let's draw the tree that we had before. Um, okay, so what happens if you've got two children? Um, and we want to erase this one. So this node has got two children. What needs to happen? Again, being consistent, pointer here is a pointer reference. So what we need to do is we need to pick the replacement for pointers. So we need to pick the see, maybe I should back up a little bit. So if you've got a binary tree, so let's actually draw an example of a binary tree. So I think it was one of the ones that we had earlier. Root has got this special property that it perfectly divides the tree into the subtree in which everything is less and the subtree in which everything is greater. And so root couldn't just be replaced with any number, right? Because if we put, let's say we tried to put 93 here, now we've broken the tree because we've got something to the right of the tree, which is now less than, and that breaks our tree rules. So in a binary search tree, and let me actually flesh this out just a little bit more. So we got 30, 15, back to what we had before. So in a binary search tree, there's this interesting property that if we wanted to replace this root node, we can't just randomly pick any of these nodes to take that place, because the node that we do pick has got to be perfectly sandwiched in between being less than everything on the right and greater than everything on the left. And so in a binary search tree, there's this interesting property that there are only two candidate nodes that can be swapped with the root while still preserving the structure of the tree. And as you can see in this case, the candidate nodes are going to be 30 and 50. And just if I plug those in, then that becomes obviously true. So 30 in this case is in fact greater than everything on the left and less than everything on the right. Or we could have picked 50. Erase this. We could have picked 50 as well. And that, again, satisfies these requirements. So that is a little motivation for what happens when we have two children, is that we're actually going to promote the in-order successor, which in this case is going to be this node. And we're going to copy its data over. So I'm just gonna color this this node to make it clear. We're going to copy this data over, which is a quote unquote swap that's happening. And then we're going to remove this node from the rest of the tree. So once we've done the swap, now we're going to recursively call erase, looking for this key. So key of minimum, or I guess maximum of the, no, it's minimum. Key of minimum in the, so this is pointer, in the right subtree. Right. So this is maybe a more in-depth explanation. We're going to have to actually find this node. So find this using the min function on right subtree. And then once we found this node, we copy it over here. and then we recursively are going to call our erase function. And this node here, the minimum, could have either no children or it could have one child. So instead of actually writing the logic to handle what needs to happen with it, just recursively call your erase function and search for it. And then that way, a logic that you've already written here is going to take care of it. And then once that happens, this should be erased, uh, and everything should be good to go. So that's erase. Probably the second hardest part of this assignment, right behind print level by level, which we will talk about soon. So this up to where it makes sense. All right. So sorry for talking so long, y'all. Thank you for bearing with me. Um, Also worth talking about is clone and move. So clone is going to be this helper function that essentially is going to complete your copy constructor and your copy operator, and then move will be, relatively kind of intuitive. So let's see. So let's go ahead and talk about clone. So clone is going to be a pre-order traversal. So like we talked about with post order, so we've got some function pre-order, and let's give it a pointer. So your actual function call, so actual function call, so whether this be a print statement or an allocation, happens before, so pre-order, you traverse through the left and the right. If you structure your traversal in this way, then you're guaranteed to do the function call before you perform that call on any of the children, which in this case is going to be very much well suited to copying a tree. So imagine we're defining our clone function and we've got some old tree which has some existing data in it, and then we've got a new tree and we want to copy this data to the new tree. Well, we don't want to start with the elements down here because we need to make sure that we have those connections coming in from the predecessor nodes. So ideally, when we copy, we'd want to copy starting from the top, and we don't want to copy any node. We don't want to copy any node before its predecessor, right? So therefore, we do the actual copy and then we look at the children. So it'll always happen in the correct order. So assuming that you use a pre-order traversal to build your clone function. So in this case, that's going to look something like your actual clone goes here. So we call this allocate new node. So if you do your clone function, something like that, then that should have the effect that you're going to start here and you're going to allocate a new node, and then you're going to move this direction and this direction, and so on and so forth. And I hope I'm getting this exactly right. Apologies, y'all, if I mess up a little bit. And as you can see, that completely constructs the tree. So this is basically what you want to do for your copy. So let's just say slash, let's go ahead and, so clone slash copy. And then for move, you're going to have a similar idea. Not similar idea, but an idea that's kind of reminiscent of what happened in PA3. So assume you've got some old data structure, which is some tree that's got some data, and we want to move this data as efficiently as possible. Let's say that this is our underscore root pointer points here, and we've got a new tree with a new root that points to, at the moment, it points to nothing because it's null pointer. We basically just want to swap these. So we just want to say that the new tree gets access to the old data and that the old root gets access to nothing. And then of course you need to update the sizes too. So think about size and think about the size. But as you can see, basically in constant time operation, by switching these pointers, we've just given the new tree access to all of this data and the old tree is reset. So that's move. And I know I'm booking it, so sorry that by the time you've implemented all the functions that I've talked about, your binary search tree should be completely working by now. The last thing to talk about is going to be the print level by level function, which in my opinion, is the most difficult part of this assignment. So let's look at it. Print level by level. You get your own, where is it? You get a very nice detailed description of what needs to happen for this function. It's essentially going to be breadth first search. And what's expected is that if you have a tree that looks like this one, you're going to print out all of the nodes as well as all of the null pointers, such that each level should be an increasing power of 2, right? So we're going to print out this node and then this node, and then we get to this level where we've got 1 null pointer, 8 null pointer. We're going to have 1 null pointer, 8 null pointer actually get printed explicitly. And also they expect you to print out the first and second values of the pairs. So whereas this tree right here represents how we sort the tree, which is, remember, element dot first, we're also printing out the data, which in this case is element dot second, which should have no impact on like, like 1, I mean 0, 1, 2, 3, 4, 5 shouldn't be meaningful to the actual structure of the tree. So to help you implement this, I have written some pseudocode, which is here, I think. Yeah. So here's the pseudocode that I've written that I think is pretty helpful. This should be more or less what you want to do to implement this function. So let's just go ahead and walk through this real quickly. So you're going to need some helper variables. So you're going to need a pointer that you use to basically interact with a queue, which is going to be storing pointers to the tree. You're going to need some kind of output string stream. It doesn't have to be a string stream. That's just how I like to think about it. You're going to keep track of how many nodes are in the queue that need to be popped at each level. And then you're going to have some kind of Boolean flag to determine when you stop the actual printing. So if we look in the code right here, print level by level is going to pass you a few things. So first, it's going to pass you a binary search tree. So you actually get a binary search tree as an input to this function. It's going to give you an O stream, which in this case is out. It's default designed to be C out, but this could be, any stream. So this could be like a file output also if you were to pass that. And then so given this binary search tree and this output stream, you are expected to traverse the binary search tree and print the nodes to the output stream. So let's look at how this happens. So the first thing we do is we're going to push the root of the tree to the queue, and we're going to initialize the size to be the queue.size. And what size means in the pseudocode is how many things need to be popped from the queue at each level. So size will be the number of elements per level that we're looking at, which will be initialized to 1, and then it'll be 2, 4, 8, 16, so on and so forth. And we're going to have a while loop and a for loop, and there's also pseudocode that exists on Canvas on the slides. So if that's more helpful to you, do it that way. I think that code is terrible, which is why I made this, my own attempt at it. But anyway, so we are going to set isNull to true. IsNull is a Boolean flag that says, have we found a non-null node yet? And if we haven't, then this stays true. And maybe some more motivation is that we have to determine when we stop traversing the tree, right? Because we don't want to print all of the null pointers in the last level. So theoretically, there's another level to this tree that is just twice as many null pointers. We don't want to print that one. And in fact, if you do print it, you'll be failing the test cases on the autograder. So we need to figure out when it is we should stop, and we should continue this iteration. As you can see, there's a check down here, so long as isNull is set to false at some point. So we'll talk about that. Anyways, basically, we just assume that we haven't found a non-null node yet. So assume that that's true, that everything we've seen so far is null. For I is going to be basically iterating through size. So again, size being the size of the level, it's going to start at 1, and then it'll be 2, 4, 8, so on and so forth. We're going to pop a pointer off of the queue. If that pointer is null, then we're going to add the null pointer or a string that says null to our string buffer, and we're going to push 2 null pointers to our queue. So that would be like if we popped this X off the queue, then we're going to add it to our string buffer and then push 2 more. And then likewise, if the element is not null, then we're going to push the actual elements. In this case, it's going to be parentheses, element.first, comma, element.second parentheses to our string buffer. We're going to set our flag to false, being that we did in fact find something that was not null. So isNull is false because this row is not null. And we're going to push that pointer's left and right element to the queue. Once we have gotten through size, so we've gone through, in this case, one iteration for the first level, or two iterations for the second level, or four iterations for the third level, whatever it is. We're going to check. If we didn't find anything that wasn't null, so being it's just a level of null pointers, then we want to exit before we print that level to the output. Otherwise, we are going to turn our string stream into a string and send that to our output along with a new line and reset our string stream. Also, what we need to do is we need to reset the size to be q.size. So imagine if the size initially was 4 for this level that we traversed, then we must have pushed 8 elements. So we set size to q.size so that next time we go through this iteration, it'll be 8. So that's the pseudocode in a nutshell. Just quickly, I'm going to walk through an example of this on my iPad to make it just doubly clear what's going on. And that should be the last thing. So, all right, so it's the print level by level. All right, so again, hopefully you had enough of a look at the pseudocode to kind of understand what's happening here. But let's go ahead and draw a tree. So let's assume that it looks like this. And let's say maybe we've got null pointers here, but maybe this one is legit. Okay, so we've got a tree that looks like this. For completeness sake, let's just fill in the rest of the null pointers. So we're looking at a tree like this, and this is what we want to print, essentially. We don't want to print the last level of all these null pointers down here. There's twice as many as the last level, 16 of them. We don't want to print that. We just basically want to print everything that exists in this tree right here. And so what I like to do is I like to make a little table that kind of represents the pseudocode that we just looked at. So we're going to have something that keeps track of the is null. So we're going to make a column for that. We're going to keep track of size. And again, size just means the size of the current level, being 1, 2, 4, 8, so on and so forth. And then we're going to actually show what goes in the queue at each level. And then also I'm going to keep track of what gets printed. So the pseudocode should initialize the queue to have the root element, which means that the size of the first level should be 1. And we're going to go ahead and set this is null flag to true, meaning that we should exit after this level if this flag isn't then changed to false at some point. So basically we iterate through size. So it's one iteration where we pop an element from the queue. We print that element, so A, and we push its children, so B and C. Because the element was non-null, we're going to set this to false, which means we need to do another iteration. So is null will be reset to true. Size will be reset to the size of the queue, which in this case, as you can see, should have doubled. So that would be 2. And Q contains B and C. And we're going to basically do that same process again. So we're going to pop B and print it, push both of its children, which in this case are null pointers, and change this flag to false because we found something that's real. Let's go ahead and iterate again. So that'll be our last iteration. We're going to pop C, push both of its children. And so now that we've reached the end of this size is the for loop, we'll be running for size right here. So once size is 0, that's the end of the for loop. And because we've set our is null flag to false, we actually go ahead and print these things to the output and continue. So we reset. The size of the queue is now 4, and it looks like this. So let's go ahead and pop a null pointer. Let me do this. So actually, yeah. So go ahead and pop a null pointer. So we'll print a null pointer. And notice we don't actually set our Boolean flag to false because we didn't find something real yet. We pop another null pointer. We pop, oh, and back up. I forgot to mention, when you pop null pointers, you still push null pointers to the queue, and that's actually super important. So, let me just go back in a little bit more detail. So when you pop a null pointer, you still have to push 2 null pointers to the queue. So again, sorry for that, a little gloss over on my part. So we're gonna pop these. Now we're going to pop D, which is not a null pointer. So we're going to set this flag to false. It's like that. And then for our last iteration, we're going to pop E. And let's see, so D was should be that. Okay, and because this was false, we're going to have one last level. As you can see, it's going to happen 8 times, and we're going to have 1, 2, 3, 4, F, 2, 3. So basically, we're just going to keep popping these things, so that'll look like if we go here, so. And then we're going to pop F, so this will be false. And we're going to pop the last 3, so just know that this is a lot. And we're going to go one more time, 16, and we're going to have 16 null pointers here, and we're going to iterate through these. This flag will never be set to false, and we're going to stop, and we will have printed this, and that's your level by level traversal. So again, sorry about the mix-up for the null pointers thing. I've been talking for too long. And if you've watched this video, hopefully you've gotten something useful out of it. Let's just go over the pseudocode one more time now that you've seen the diagram. So we're going to have this temp, which we use to manipulate, well, not manipulate, but store the last pointer that we pop off the queue. We're going to have a queue of pointers that stores the pointers that we need to print. We're going to have some kind of buffer that we use to keep track of what needs to be printed. We're going to keep track of the size of each level, and then we're going to have a Boolean flag for whether or not we need to quit that level. We're going to initialize the queue by pushing the root and set size is equal to 1. So basically, until we've found proof that the level is non-null, we're going to say that the level is null. And then we're going to loop through the size of the level where we pop something off the queue one at a time. If we pop something null, then we're gonna add null to our string buffer and push 2 null pointers. Else, then we are going to print the element at that pointer, reset our flag to false, being that you should actually print the buffer to the output and then push both the left and the right pointers. Once we've gone through the entire level in the for loop, if we haven't found something that was non-null pointer, we exit. Otherwise, we reset the queue size so that the next for loop is going to run twice as many times, and then print the buffer to the output and reset the buffer. So that is a lot of information. That was a lot to throw at you. Hopefully, you were able to find some kind of use from all of that rambling. Say that the most important concepts that were like super difficult, probably the pointer reference thing, the print level by level thing, maybe recursion to some extent. But if you can get those, you are well on your way to understanding trees. And take it from me personally, this is my favorite data structure. The tree comes up everywhere. You want to nail this assignment. You want to like really figure it out. But if you have questions about anything I didn't talk about or something that I should have included in this video that I didn't, please reach out to me and email me to make these videos better. Or if you see me in person, say what's up. Let me know what I can do to make these more helpful. Yeah, that being said, best of luck, y'all.